Hello everyone. So we'll start our discussion uh, or we'll continue our discussion on strain, but we'll start it off with where we exactly left in the last time. So we had found out that under the consideration that del u by del xj magnitude is much less than 1, we obtained this. So we want to use this expression and proceed from here to again go back to, if you remember, our original definition of engineering strain and perhaps obtain some useful expression for it. So under these new considerations, so we'll start from this expression. Okay, so what we have on the left hand side is, as before, del small x vector magnitude square is equal to del capital X vector magnitude square plus twice d xi d xj, both capital X, and epsilon ij, the small or the infinitesimal strain tensor. Now what we want to do is we want to introduce the unit vectors corresponding to these dxi and the dxj. So we understand that this dxi, it is a vector and it has a certain magnitude, which we again understand to be nothing but this itself, the dx vector magnitude without the square. Now if we want to represent this general vector in terms of its magnitude, then we should also be able to isolate out the unit vector which represents its direction. So what I mean is that let's go to the rough column and discuss it very simply. So back in your high school or maybe first year, so when you wrote a vector like this, so you could write it like this, the same vector magnitude, but some kind of a unit vector which is along the direction of the a vector. So you see, this unit vector, it captures the direction of this vector, and this magnitude, it captures of course the magnitude of this vector. So this is the same idea that we're going to utilize here. So dxi or equivalently dxj, that will be equal to dx vector magnitude, because this is nothing but the dx vector itself, and that should be equal to the unit vector along the dxi. So where ni is the unit vector along dxi. Okay. Similarly, we have for dxj, d capital X vector magnitude nj, where again nj is the unit vector along dxj. So if we use these ni's and nj's, so what do we have? Dx vector magnitude square is equal to the same thing as before, d capital X vector magnitude square plus we obtain a dx vector magnitude from here and another dx vector magnitude square from there. So overall we have dx vector magnitude square, and then ni, nj, epsilon ij. So exactly the same thing as before, but re-represented in terms of the unit vectors. Now note that this particular combination ni, nj, epsilon ij, as before, it has no free indices. So earlier we had this particular combination, here also we had no free indices, here also we have no free indices. So both the I and j are repeated, and this particular combination is a scalar combination. But is it perhaps possible to express this particular combination in a compact or a vector notation? So the answer, of course, is yes. We can always find an equivalent representation, and that is Ni and j epsilon ij, that is equivalent to n unit vector transpose dotted with epsilon dotted with n unit vector. So if it is not very clear to you how this is coming out, you can perhaps rethink about this in terms of components like this. So n1, n2, n3. So what I'm doing is I'm rewriting this or re-representing this in terms of the matrix notation. So this is equivalent to you see this entire thing written in a very compact notation is rewritten in the matrix form in this kind of form. And please note that this is not something new to you. Back when you were studying, I believe your mathematics 2 in your second semester of first year, you came across something called the quadratic form in one of the linear algebra chapters or in one of the matrix chapters. So this is exactly that. This is again nothing but the quadratic form. And please note that the quadratic form here is very much a scalar quantity. Okay, so what is the use of all this? Well, you see, we can rewrite that earlier expression. So what we are going to do here is we are going to take this dx vector magnitude square as common. So that will simplify our expression a little bit. We're going to take this as common, so we'll be left with 1 plus 2. Now we are going to write this down. This is the more compact notation. Okay, now some of you who are of a more practical bent of mind and do not want to be bothered with this much of maths and theory, you may be wondering what is the point of writing this once in terms of index notation, then again in this compact notation, and again this matrix notation. Well, you see, we are writing this as it is convenient to us for various purposes. So it is a very purposeful kind of way of approaching the subject. So when we are writing this down either on a piece of paper, or here I'm writing on a digital board, we are basically manipulating algebraic symbols, and there it is a little bit easier to deal with this index notation, but ultimately when you have to solve problems, not just for the purpose of your examination, but in a more professional environment, whether it is for engineering research or actual professional engineering field, you will see that you will always have to ultimately resort to computers. And when you are dealing with computers, you ultimately have to make the computer understand things in terms of matrices. well, usually. So uh, so that's the purpose here. As far as the algebraic manipulations are concerned, we want to do the algebra in as simple a form as possible, writing as few symbols as possible by taking the help of the index notation. And then we also want to re-represent the thing in terms of matrices, so that later on when we have to make the computer understand, then we can easily feed the values as desired in this particular form. Okay. Uh, Now, as I had told you earlier, the motivation of proceeding in this line is to ultimately obtain a simplified expression for the engineering strain. So remember, we had started this entire section on strain by defining the engineering strain. So how can we go back to that? So let's take a quick look at the engineering strain. If we go back a few slides, you see here uh, we have the definition of the engineering strain here. You see, it is very much involving the d small x vector and the d capital X vector, but in a slightly different fashion. And because we wanted to avoid the use of square roots, we had taken these squares, and that is why we are still stuck with these square roots, with the squares, but we want to get rid of it. And you'll see that you'll see in the next slide how we can do that. So I'm going to carry over this expression to the next thing. All that I'm going to do is I'm going to divide throughout by d capital X vector magnitude square. So this thing I'm going to divide here. So this is equal to, you can see this is just 1 plus 2 n unit vector transpose dotted with the strain tensor dotted with again the n unit vector. Now if we go back to the definition of the engineering strain, so we want to utilize this expression, but we know that the engineering strain is equal to this, which implies that d small x vector magnitude divided by d capital X vector magnitude is nothing but 1 plus epsilon e. Okay, so if that is true, then this is nothing but the square of this, which means that we simply have this thing to be true. 1 plus epsilon e, the engineering strain whole square, is equal to 1 plus twice n vector transpose n unit vector. Now we are almost done with this derivation. We just have to employ one more trick. So you see, we can expand this very easily like this. Very simple. But overall, we are considering very small deformations. Overall, we are working under this assumption that this is small. So, small deformations. Now, if the deformations, overall the deformations are very small, then this implies that epsilon e is also expected to be small, which implies that epsilon E square can be neglected. In the previous expression. Therefore, for all intents and purposes, what we have is 1 plus 2 epsilon E is approximately equal to 1 plus 2 n hat transpose strain dotted with strain tensor dotted with this. So overall, what we just obtained under this approximation is that this is, so I'm with a little bit of abuse of notation, I'm writing this approximately as equal to, because we understand that we are working overall under small deformations. So this is just this. Okay, now this expression that we have obtained, it is an extremely important and extremely useful expression. This one, you note it down very, very carefully. So you will see that in quite a different variety of problems, as well as for our theoretical developments, as well as for theoretical kind of problems, this is very, very important. And ultimately, this is the engineering stream. So let us try to interpret this a little bit before we end this part of the lecture. So what is actually happening here? So suppose, so this is the physical interpretation of this. So suppose we have a general three-dimensional body. Let us go back to that discussion. Okay, and we are considering any general point within it. Fine. Now we can set up a certain coordinate axis here, no problem. Let us say we have got this system of coordinate axis. So x1, x2, x3. Now refer to this coordinate axis, we will have a certain displacement field under the presence of some kind of loading. In this chapter, we don't care about what loading there is, but we understand that there will be some kind of mechanical loading over this body, and under the effect of that loading, this body is going to deform this way, that way, whatever, and some kind of displacement field is going to be established in it. Displacement field means just a description of how the deformation has taken place as it goes from this undeformed state to some deformed state. That much we understand. I'm not going to draw the deformed state again here. So you understand that this itself is the deformed state. Fine. Alright. Now if this is the deformed state, there is some value of u1, u2, u3. Not at this point. If you take another point, there will be another value of u1, u2, u3 correspondingly. So suppose instead of x1, x2, x3 you take x, y and z, you will have different values of u, v, w. So no matter what way you look at it, you will obtain different values of u, v, w at different points all throughout the body, and all together this is referred to as the displacement field. Very easy to understand. Okay, now if you have this distribution of displacement, okay, or displacement values, so that entire thing is referred to as the field. So so there will be slight small variations from, if you consider two neighboring points, there's a little bit of variation in u1 or u, there'll be a little bit of variation in v, there'll be a little bit of variation in w along all the directions. So if you calculate the various derivatives, you will end up with a certain value of the strain tensor components here. So let us go back to this previous slide here. So you can very well calculate the values of del u, del y, del v, del x, all these things, various values of this. Okay, I ask you, I provide you with the information about the displacement field. You know the geometry and everything, and you can find out the values of these derivatives. Of course, the understanding is that a mathematician will come and say that okay, these fields need to be sufficiently smooth and all that, but okay, for all intents and purposes, as an engineer, you understand that in usual circumstances this is going to be smooth enough. So you can find out these derivatives, and so all fields are going to be differentiable and what have you. So you can find out these values, which means that all the strain components that are present here, the epsilon 1, epsilon 2, epsilon 3, the rest of them, equivalently epsilon xx, epsilon yy, epsilon zz, you can find out. Fine. So if we come back to this picture, basically the picture that you have in your hand is this. You are sitting at this point, and at this point you know the various values of the strain components. Fine. Which means that in this formula, this entire formula, you know the 6 independent components of the epsilon. Fine. Next, what you do is you ask the designer or your customer, maybe, like in which direction you are interested in finding the engineering strain. Okay, so this is like a hypothetical engineering question I'm asking you. It's going to be far more complicated than that, but let's say the person says that, okay, you tell me the engineering strain in that direction. That direction means a direction which is maybe at 45 degrees to the x-axis, at 60 degrees to the y-axis, and some angle to the z-axis. Okay, so in that particular direction I want my engineering strain. So all that you have to do is put the direction cosines of that unit vector here. Similarly here, do the entire multiplication. How? Just by going back to this formula. So here you see, you know all these values because you have already calculated them at that point, and then as desired you put the different values of the, so this n1, n2, n3 are nothing but the direction cosines of the desired direction along which you want to find out the engineering strain. So you put down the different values, and then you just have to do this entire multiplication, and you will end up with a single value. So this is a second order tensor, this is a vector, but ultimately when you do finish the calculation, you will end up with a single value, and that single value is going to give you the value of the engineering strain. So what we say is that the engineering strain is the strain along a particular direction given a certain displacement field in the three-dimensional body. That is all there is to it. So this is how and this is how the connection is also established with what you have been studying earlier. So earlier what you are saying is that, like in your first year classes, or maybe even earlier in your high school, that you are going to measure the initial length and the final length, and then through a little calculation you can find out the strain. So all that is fine if you have a very simple kind of one-dimensional body, but in a general three-dimensional body you have to take care of the various directions, which is why we had to take all this trouble to finally arrive at this nice compact notation. Okay, so these are very, very useful, very general, very much dependent on the mathematical framework, but ultimately very useful for engineering purposes, this formula. All right, so we'll continue our discussion of kinematics chapter in the next part of the lecture, but as far as the strain section is concerned, we are done with it. There will be some very interesting problems in the problem sheet on this. Okay, thank you very much.